pivots dash numerical catastrophe. Small pivots dash numerical catastrophe. Consider with 3-digit decimal arithmetic. Like, let's consider this matrix. Now it has 0.0001, and then we have 1 here, 1 and 1. So when we have a pivot that has a very small values as seen on my screen, how do we deal with this situation? Now imagine you're trying to get your multiplier, and then you divide your multiplier. You see one. Remember, the goal is maybe trying to uh, reduce this pivot to 1, okay, and make this guy become 0. That would be the goal, right? Why is this not clean enough now? What's happening? Sorry, this my marker has started again today. I just want to clean up. Okay. Ah, let's continue. Let's continue. I don't want to waste time with this. So when we obtain the multiplier is M21. That is, we pick the 1 from this guy, we invert this 1 over 0.0001. That's simply 10,000. When you divide this value by 1, or 1 by this value, you get 10,000. Now after elimination, this is what we are going to get. A22, that is this value here, will become 1 minus 10,000 times 1, which will give negative 9999, and that's approximately equal to 1.00 times 10 raised to the power 4. This is 3 digits. Then our B1, which is this value right here, B2, rather, B2, that is that value, that becomes 2 minus 10,000. That will give negative 9998, and that value is approximately equal to minus 1 times 10, minus 1.00 times 10 raised to the power 4. By the time we attempt to back substitute, if we want to perform our back substitution, what we will obtain will be these values. We have x2 as 1, we have x1 as 0, okay? And with that value, it means that the computed solution that we've obtained is 0,1 with the transpose 0,1. So this is the solution. But when you solve this problem using the normal substitution or elimination method that you know before now, the exact solution that you obtain is 1.0001 or 0.99999. As you can see, this solution is approximately equal to 1.1, which is not. So you can see obviously that 1,1 is not equal to 0,1. When we solve it using the pivot, the small pivot, we obtain 0,1. But when you solve using the exact solution, we have 1,1 approximately. In that case, we need to calculate the relative error. Remember, we dealt with error in the last class. What is the relative error? The relative error is the difference between the actual solution, that is 1,1, minus the estimated solution 0,1 divided by 1,1. That is, you take the norm of all of these expressions, right? By taking the norm of the numerator, 1 minus 0 is 1, 1 minus 1 is 1. So you have 1,1 over 1,1. Sorry, 1 minus 1 is 0, 0. So this is what we get. Okay, now, and that's exactly what we have here. So when we have this, the next thing is to compute the norm. Don't forget that the norm is simply 1 squared plus 0 squared, the square root of this. That is the norm of the numerator. Then the denominator, the square is, or the norm is also 1 squared plus 1 squared. So 1 squared is 1. 1 plus 0 is 1. The square root of 1 is 1. And here, 1 squared is 1. 1 plus 1 is 2. And then we have the square root of 2. okay, which is what we have here. And if you calculate it in percentage, when you evaluate 1 over the square root of 2, you will notice that it's approximately 71%. So what it means is that the relative error for solving a system of linear equation with a very small pivot is very high. 71% being an error, a relative error, is kind of a disaster. So despite that the matrix being well continued or conditioned, so our matrix was well conditioned, we're able to obtain an answer, but you see that the error is massive. So if you have a very small pivot, then there's also a problem. If you have a zero pivot, there is a problem. So what do we do also in this case? When you have such pivots, what do you do? The same solution as applied as above is what we're going to perform. Interchange rows first. Once you interchange the rows, then you have the solution as expected. This gives a correct result even in 3-digit arithmetic. What are the lessons learned from this? Number one, small pivots amplify rounding errors, and they are catastrophic in solving such system. The multiplier m of ik equals aik over aa over akk can be enormous. That is enormous. Enormous. That is when you take the norm of akk is as a very tiny value, and this can lead to three things. Number one, the loss of significant digits in row operations. Number two, cancellation errors. Number three, completely wrong solutions. So when you are faced with this situation, what do? Choose the largest available pivot at each step. Before you start, choose the largest available pivot. Don't forget this step I just said, because we are going to apply it very soon. Now look at this example that we're going to treat here. But before we go to the example, let's talk about partial pivoting strategy. Partial pivoting strategy. I believe you guys are writing it. If I'm too fast, let me know. I'm trying to cover a lot. So please just let me know if I'm going too fast. Partial pivot or pivoting strategy. Now, what's the idea? Yes. Go ahead. Let me hear you. Someone's mic is unmuted. Does anyone want to say something? No, I suppose. What is the idea? Definition 2.1. Definition 2.1. Definition 2.1. Okay, partial pivoting. At step K of elimination, before using the component A subscript KK as pivot, what do you do? Step 1, search column K for row K to row N. For the entry with the largest absolute value, that is the first step. Just pay attention to these steps. We are going to practicalize it on this call. Once you do that, what's the next thing? Interchange rows to bring this entry to the pivot position KK. When you look at your matrix and you see that there is a value which is the pivot above that is smaller than the pivot below, look at other entry or other rows of that matrix and then pick the pivot with the largest number. Then you simply interchange. That's what the first step is saying, and the first and the second step. Then you proceed with the elimination using the new this new pivot. That is step 3. So this is called what we just described here is called the partial pivoting, because we search only within the current column, not the entire remaining submatrix. We only search within the current column for that pivot. All right. Remark 2.1. So why partial? Why do we have to work with partial? Now we work with partial pivoting to search for column K only. This is what we do actually. Then the complete pivoting search for the entire remaining submatrix. That is, this is very expensive to perform, and it is rarely needed. So we don't have to always do the complete pivoting. What is most important is the partial pivoting. Then in the case of no pivoting, we use the diagonal elements as is. Now, what we did in week 1, that is the solution we solved in week 1. So this is just the visual illustration of the partial, pivoting that we're explaining. But let me just go ahead and explain it in an example. Okay, so let's take this example 2.3. For we apply the concept of partial pivoting to solving this problem. Example 2.3. Okay, so I would like to hear someone read this matrix for me quickly. James, unmute your mic and read the matrix that you see on the board. So let's start with the matrix of coefficients. Just tell us the numbers in the matrix of coefficients quickly. James, if you can hear me, give me thumbs up.
Okay, yes, sir.
Okay, go ahead and read the matrix of coefficients because you unmuted the mic but you didn't say anything.
Sir?
Read the elements in the matrix of coefficients for the example 2.3.
I'm not seeing the screen, sir.
Jonathan, can you read the matrix of coefficients for me, the example 2.3?
Okay. But it disappeared just now, sir.
Okay, it shows now.
Okay, that means it's you guys' network. It's not my network. My network is stable. Go ahead.
Is it step? Say what? What step, sir?
Tell me the matrix of coefficients. What are the elements in the matrix of coefficients in example 2.3?
You're trying to say 1, 2, 3, 2, 4, 1, 2, 1, 2.
Okay. Although I can't get who said that, but you're correct. The matrix of coefficients is 1, 2, 3, 2, 4, 1, 3, 1, 2. Then the variables are x1, x2, x3, and the constants are 6, 7, 6. Now looking at the steps that we highlighted above, let's look at the steps. Look at this first step. The first step says search column K, right? From row K to N. At step K of elimination, before using this as pivot, search for the entry with the largest absolute value. That is, what is the pivot here? The pivot here is 1, isn't it? Is that correct? The pivot there is 1. Give me thumbs up if you agree with me, everybody. I hope there is no one sleeping in my class. Abubakar is here. I've not gotten thumbs up from Jonathan. Okay, Charles has given me his thumbs up. Mustafa, I see your thumbs up. Joseph, I see your thumbs up. Okay. Now, that is it. Then, but since 1 is not the largest number, we are going to find a pivot column. So column 1, the values will take the absolute value. So whenever you see this, you take the absolute value of all the numbers on that column 1. The absolute value of 1 is 1, the absolute value of 2 is 2, and the absolute value of 3 is 3. And that's exactly what happened here. Then the largest value from all these 3 is what? 3, which is also in row 3. So what do we do? Because that's the largest value, we then interchange rows 1 and 3. Take row 1 to row 3 and row 3 to row 1. And that has to be done for every other, every other element in the same row. All right. So once that interchanging has been done, look at what then happened. We proceed with pivot A11 to be equal to 3. Then the multiplier is going to be M21. That is, you are going to multiply the element at the second row by that in the first row. That is 2 over 3. That is M21. Then M31 is take the element 1 in the third row and divide by the element 3 in the first row. That is 1 over 3. Okay, so these two values here are the multipliers that we're going to use to multiply row 2 and row 3 to reduce this to 0 and this to 0. And immediately that these multipliers were applied, this is what happened. We're multiplying each of these by this fraction. Then when you multiply the first one, we got 0. Yeah. And then multiply the second and do your addition. That one gave us 10 over 3 multiplied. So what's happening here? Can someone tell us what's happening there? You see, what we're doing is we're saying that we're going to, for R2, we are replacing row 1 minus 3 over 2, or 2 over 3. 2 over 3 R2. Did you get that? Row 1 minus 2 over 3 R2. So the first one, 2 over 3 times 3, that is 2. Then 2 minus 2 will give 0. That's how we got the 0 here. We then performed it for all the elder entries, and we arrived at this number. Then the last row, which has 1, 2, 3, x3, and 6, we also performed the same operation. This same operation here, and reduced the last row. The pivot, the last element is 0, and everything has been reduced. Okay, so since that is done, what should be the next step? We go to the next column. We look at this second column here, and we find the pivot in column 2. The pivot is in column 2. What are the values? What the column 2 values? That means we divide each of them by just get the absolute value. So the absolute value here is 3.33. The absolute value here is 1.67. So what do we then do? Latest, of course, we have A22, 10 over 3, which is already in position 2. And now, when you interchange is needed, proceed with eliminating using the pivot 10 over 3. So when you use this pivot 10 over 3 and you eliminate, this value here will become 0, and everything will also balance out. So with that, you obtain the answer to the problem. All right, and that's what partial pivoting is actually referring to. If you understand the concept of partial pivoting, can you give me a thumbs up? If you understand the concept of partial pivoting, give me a thumbs up, please. Mustafa, let me hear you. You're giving me thumbs up. Let me hear a question. Please ask me.
Sir, please can you come again for this row 2 that you say row 1 minus 2 all over 3 row 2?
Okay.
I'm
This-
just checking the mass.
This one. Okay. When you
Row 2
multiply
that
when you multiply 2 over 3 by row 1, you have 2 over 3 times 3. That is equal to 2. We have 2 over 3 times 1. You know this is 1 here. This one. That will give us 2 over 3. We have 2 over 3 times 2. That will give us 4 over 3. And then we have 2 over 3 times 6. And that will give us 4. So once that is done, what you need to do is to subtract it from row 1. Yeah? Subtract. I hope I've done the correct thing. Sorry. I was supposed to multiply these guys here. This one. This is my board. This is my English clean now. Why is it doing this? Okay, it's cleaning now. Just wanted to stress me.
sorry sir.
No, not you. Is this my board? I want to stress me, not you. It's cleaning. Just be patient, so that I can show us again the solution that we obtained here. Now look at the elementary row operation that was performed. Okay, that was performed. To obtain this one, R1 remains the same, nothing happened to that. But to get this, what we did was we said R2 should replace R2 minus 3 over 2 R1. That is, you multiply 3 over 2 by 3, 1, 2, and 6. In fact, sometimes you don't have to consider the 6. Just use the coefficients. When you open the bracket to multiply, no, it should be 2 over 3, not 3 over 2. 2 over 3, right? 2 over 3 and not 3 over 2. So now this is
Sorry, sir. Before it was R1 minus 2 all over 3 R2. That is right.
sorry, it's 2 over 3. That was a mistake. 2 over 3. Now if you multiply this will give you 2. This will give you 2 over 3. This will give you 4 over 3, right? That's what you get. And you now subtract it from R2. So R2, what is R2? You have 2, 4, 1. When you subtract 2 minus 2, 0. That's how God is 0. Okay?
Yeah.
When you subtract 4 minus 2 over 3, 4 minus 2 over 3. Find the LCM 3. 3 and 3, 1 times. Sorry, 1 and 3 times this, 12. 3 and 3, 1 times 2. 12 minus 2, 10 over 3. That is what brought me here. Then 1 minus 4 over 3. The LCM here is 3. This is 3 minus 4. And that is minus 1 over 3. That's what brought us here. And so on and so forth. Do you understand it now?
Yes, I understand.
Good. So that is what brought us there, and so on and so forth. Now, with that said, this should make you understand when to use partial pivot, and yeah, and you'll be good. All right. Does anyone have something to say? Nobody. So I will be leaving all the algorithm aspects. I will leave them until we meet physically, so that we don't waste so much time. Until we meet physically in school, then we can solve most of the problems with solving manually using computer. So I'll also leave this computational cost part. We will discuss it when we meet physically. This class governor remind me, I have it in mind. Let's quickly talk about LU decomposition. This is LU decomposition. The upper, it's like the okay. We'll talk about what the LU stands for: lower and upper triangular matrix. There's LU decomposition. So what's the fundamental idea? Here is the fundamental idea in terms of key observation. We notice that the Gaussian elimination implicitly factors the matrix as A equals LU times LC, or just say A equals LU actually. So that is what the Gaussian elimination implies. Now, what is value? What is L rather? Where L is a matrix that is L is a lower triangular matrix with ones on diagonal. U is an upper triangular matrix. Then, when you talk of the factorization, say this factorization is extremely useful. Here, this factorization here we have is extremely useful. This is where we say by getting this upper and lower triangular matrix, we can then go ahead and say, okay, let us have solve AX equals B, right? We solve, this is where we solve AX equals B. And we solve AX equals B, and by solving these two triangular systems, that is, we use the L and we have to reuse the L and U for the multiple right hand sides. Then we compute the determinant of A, the inverse of A efficiently. So these are the steps that we're taking when we try to use the Gaussian elimination with the lower and upper triangular decomposition. Are there questions? Who is sleeping in my class this night? Nobody should sleep. Oh. Moses, are you still on this call? All right. I hope you guys understand what. Who is Philo? Who is Philo? Wake up! Oh. Don't sleep. If I catch you sleeping in my class. So let's look at an example. All of these stories we've said. Let's put it together in an example. Or instead, before example, let's look at a definition, a proper definition. Please write. Right, definition 2.2, LU decomposition. An LU decomposition for, or so it's either we call it LU decomposition or we call it LU factorization. So when you hear the word LU decomposition or LU factorization, they mean the same thing. So an LU decomposition of any n by n matrix is a representation of A equal to LU, where L is the matrix that is presented like this: 1 0 0 0 up to the n 0, L21 1 0 0 0 0, L31 L32 1 0 0 0, up to LN1 LN2 LN31. So if you look at this, you see that throughout the diagonal, 1 is presented through the leading diagonal, and then every other element above it will become 0, and all the elements below will become non-zero real numbers. That is the lower triangular matrix we're discussing, or we spoke about. While for the upper triangular matrix, we are interested in having just the natural upper triangular matrix where all the elements below the leading diagonal is 0. So in this case, we are not particular about having 1 throughout the elements in the leading diagonal. So we are not particular about having 1. So 1 can be part of those numbers. It can be 2, 1, 5, 7, stuff like that. But we are not particular about having 1 throughout. But in the lower triangular matrix, we need 1 to be in the leading diagonal. Does that make sense, guys? Give me thumbs up if you understand. If you understand the way to present an LU decomposition, then give me thumbs up. I can see only Jonathan's reaction. Please, I'd like to see more reactions. If you can still hear me. Are you sure Charles hasn't slept off in my class? Charles. Okay, Charles is still awake. Mustafa, are you still awake? Okay, Joseph is here. Mustafa is awake. Ibrahim, is Bala still on this call? Bala has left the call. I trust that man. I trust Bala. If Bala didn't leave the class, his network will leave him. So it's either Bala leaves or the network leaves Bala. Let's move to theorem 2.1. Theorem 2.1. Existence of LU decomposition. So how do we tell that a matrix has an LU decomposition? Please write. If Gaussian elimination without pivoting succeeds, all leading principal minors are non-zero. All leading principal minors are non-zero. Then A has a unique LU decomposition, and then the elements are Lik equals Mik. That is the multipliers from the Gaussian elimination. Then U is the upper triangular matrix from GE. All right, that is from the Gaussian elimination. So this is the theorem that confirms the existence of any LU decomposition. Please, am I communicating? Let's take an example. Let's take an example just to portray the point of what we've said. So let's take this example 2.4. Let us perform this LU decomposition by hand. So the question says, find the LU decomposition of the matrix A, which has the elements 2, 1, minus 1, minus 3, minus 1, 2, minus 2, 1, and 2. Let us find the LU decomposition of this matrix. Can we proceed? If you want us to proceed, give me thumbs up. Give me a reaction if you want us to proceed. All right, perfect. Okay, is someone going to say something? Yeah, Ibrahim, go ahead. Or is that supposed to mean a thumbs up from you? Okay, I want to assume that is a thumbs up. Okay, that is fine. So now the solution, here's the solution. We perform recording multipliers. For example, 1.2 in week 1, we had this. Of course, you can update the multipliers again. All right, M21, and then we had M2. So what is M21? M21 simply means we are dividing the element on the second row by the element on the first row. And minus 3 divided by 2 is minus 1.5. That is L21 or M21. And M31 is we divide minus 2 by 2. And that gives minus 1. Then for M32 rather, 32, this guy, that will give 4. Okay, by just multiplying, by multiplying our what is it called, multiplier, taking the product of whatever when we resolve. So because this point you can see the form very clearly until you apply these two steps. If I apply the 2 steps that we applied from the previous example to obtain 0, 0, that is how you can see this as 4, 4. Now you can see. So if you, by the time we apply those, we perform those steps, and then we'll find the upper triangular matrix. This is what it's going to turn to. We have 2, 1, minus 1, 0, 0 0.5, 0 0.5, 0, 0, and minus 1. This is what we obtain. So some steps were skipped here. And I believe that you can all obtain the steps. We have the multipliers already. You know what to do to obtain the steps. The goal is to obtain 0, 0 here. Want to obtain 0 here, want to obtain 0 here, and 0 here. That is the goal. So when you apply these steps by multiplying each row by these multipliers, you have this matrix, and that is the upper triangular matrix. Now, therefore, if this is the upper triangular matrix, therefore it means that the lower triangular matrix is what do we do to obtain 1, 1, 1 here, and then every other number will remain the way it is. So how do we obtain that number? This is the matrix we've gotten already. All right, so the first thing to look at is, what if we take the transpose of this matrix? We have 2, 1, minus 1, then we have 0, 0 0.5, and 0 0.5, and then we have 0, let me see, 2, 1, 0, 0 0.5, 0, 0, and minus 1. Okay, if we have this matrix, then we apply our reduction, row reduction method again to make this one become 1. Yeah. When we make this become 1, the next step is make here, we make this become 1 also 0.5, and then we make this become 1. When you do that, this is what you're going to obtain. You can try that later after the lecture to save some time. So you make this become 1, make this become 1, and make this become positive 1. So we have this lower triangular matrix. We have the upper triangular matrix. We also have the lower triangular matrix. Now to check, remember that we said that matrix A is equal to the lower triangular matrix times the upper triangular matrix. That's the beginning, the genesis of all of this discussion right here in this particular module. Right, you can see it here for LU decomposition. Yes, please go ahead with the question. You can unmute your mic and ask your question, please. All right, no question. I thought there was a question. So let's look at this multiplication. Of course, I believe everybody in this class can multiply two matrices. When you are performing matrix multiplication, you are multiplying the row elements by the column elements, right? That is 2 times 1, 2, plus 0 times 0, 0, plus 0 times 0 is 0. So that's why this one is still 2. Then when you are done with that, move on to the next row, still with the second, this next column, still with the first row, move on to this column to see if we can, get the answer. 1 times 1 is 1, plus 0 times 5 is 0, 0 times 0 is 0. So that's where we stopped. Then move on to the next column to see if we're going to ask, obtain the answer as expected. What's the third column? Third column is this guy. Then we'll say 1 times minus 1, I'll give minus 1, times 0 so when we do 0 times 0, everything will give us minus 1, because this is 0, everything here becomes 0 and multiply them. And that is how we got the first element in the first row of our L times U. Then the same way we obtain the elements in the second row by multiplying this row by this column to obtain this. Multiply this by the second column to obtain this, then by the third column to obtain this. So that is how to go ahead and multiply these two things. And by the time we simplified this product, we obtained the matrix A. And this is indeed the same matrix that we started with. This is matrix A. Can you see that? When you scroll up and check, you notice that that is exactly matrix A. I haven't been able to decompose the matrix into some matrix decomposition or early decomposition. We still got back the same matrix after multiplying the lower triangular matrix and the upper triangular matrix. Are there questions? Any question? If you don't have a question, I'd like you to give me thumbs down. If you have a question, give me thumbs up. Okay. All right. Now let's write using LU decomposition to solve systems, or yes, to solve systems using LU decomposition to solve systems. Once we have A equal to LU, the next step is to solve for AX equals B. It becomes, instead of saying A equals to AX equals B, now we have A as LU already, it becomes LUX equals B. That's the system we need to solve. So in this case, we follow two-step process. That's the first substitution. We solve for LY equals B for Y, and then we solve for ux equals y for x. That's how we break this into forward substitution and backward substitution. All right, the algorithm part to the left. Let's look at this example. Here's a typical example. The example says solving with LU decomposition. Using the LU decomposition from the example that we saw in 2.4. That is this example in 2.4. This very example here, right? Using the LU decomposition, we have that ax equals 8 minus 11 and minus 8. Yeah, that's it. That's a known value. Then step 1, we will solve ny equals b. That's step 1. Ny equals b. What does that mean? We are multiplying the lower triangular matrix by the values, the column matrix of the unknown, and equating it to the constant values. That is it here. This is the lower matrix, lower triangular matrix multiplied by this. And then when you do that, you notice by forward elimination, I have y1 equals 8, because when you multiply this guy by this, you can see already that y1 is equals to 8. Then we also do the same thing to the second row. And when you do the same thing to the second row, you notice that we have y2 equals minus 11 minus 5 times 8. That gives 1. Then with 5, we do the same performance or multiplication of the whole numbers, and that also gives 1. So which means that automatically we have the values for y. So y equals 8, 1, 1. That is the 8 we have here, the 1 we have here, and the 1 we have here. And that is the solution for y. Therefore, step 2, we want to solve for x. The y we've gotten is what will now form our constant, coefficient of constant b, but we all know is y, right? So we solve ux equals y. That's the upper triangular matrix times x equals y, the same y. Which is not a bad idea. And when you expand that, we have x3 as minus 1, x2 as 3, and x1 as 2. So here we've now gotten the solution of the problem 2, 3, and minus 1. And this is very interesting. So this is how to solve systems of linear equation by LU decomposition. I hope when I give a problem that we all solve now using LU decomposition, everybody on this course should know what to do. If you know what to do, can you just give me a reaction? Okay, very good. Very good. Well done. Is there any new student on this call? Is there anybody that I have not seen before, that hasn't joined my class before, that is joining here for the first time? Who is the person? Who is joining my class for the first time? I've not mastered all your names yet. The names I know Charles, I know Olamide. Olamide, are you here? I know Jonathan, I know Moses, I know Bala. Olamide, can you unmute your mic? Let me hear your voice. Guys, Olamide has slept off. Olamide has slept off. Who is closer to her? Please, can you tap her for her to wake up? Okay, let's move on. No time to say no time. Why LU is powerful? Well, we will see all of this. Let's leave out this notes. Now let's come to LU decomposition with partial pivoting. LU decomposition with partial pivoting. Yes. Are you sure? Let me be. Okay. Let's try it quickly. Let's try it quickly. Now we're looking at LU decomposition with partial pivoting. LU decomposition with partial pivoting 2.5. Let's write down 2.5.1. Permutation matrices. Permutation matrices. When we do partial pivoting, row interchanges occur. When we do partial pivoting, comma, row interchanges occur. Full stop. We track this with permutation matrix. We track this with permutation matrix. Example 2.7. What do you mean by, or not example, definition 2.3, please. Definition 2.3. What do you mean by permutation matrix? A permutation matrix is obtained by rearranging the rows of the identity matrix. A permutation matrix is obtained by rearranging the rows of the identity matrix. Here are the properties. 1. The transpose of the matrix P is always equal to the inverse of P. And this particular theorem speaks towards orthogonality. Second property is this, that the transpose of the matrix times the matrix is equal to the matrix times its transpose is equal to I. That is not one, that is I. That is the M by N identity matrix. Then property 3 says that the determinant of the matrix P is always equal to 1. Then we have Px permutes reorders the entry of X. Now let's look at an example. Example using permutation matrices. Example using permutation matrices. So you can see here, these matrices has 0, 0, 0, 0, 0, 0. So let's use the permutation matrices method. The first is interchange rows 1 and 2. Interchange row 1 and this is what we want to do. Then when we do that, we perform the permutation matrix of 1, 3 times A. That is, we have this matrix times A. So picking the elements. So what we just did here is just comparing the general form of writing matrix. A11, A12, A21, A22, A13, A21, A22, A23, and then A31, A32, and A33. Okay. You see what we started with? Watch this. See what we started with. See what we've gotten. We took A33, A21, A11, like we just inverted it. Then A32, A22, A13. All right, so with that said, we can look at this particular theorem. We can look at this theorem, theorem 2.2. This theorem is called LU with partial pivoting. For any non-singular matrix A in the matrix of 2 by 2 square, n by n square matrix, there exists a permutation matrix P such that PA is equal to LU for every non-singular matrix A in the matrix of square matrices. For every matrix, there exists a permutation matrix P. So P here stands for permutation matrix, such that when you multiply P times A, the answer you get will be equal to LU, where L is the unit lower triangular and U is the upper triangular, matrices. Equivalently, the same thing we've said here, it has an equivalent statement. The equivalent statement is that P raised to power T, that is A equals P to the power of T times LU, and that will give PLU. It has to go through the director. Let me see. Am I communicating, guys? Hello? So, what I'm trying to say in essence is that the equivalent of this statement that is said here, we can say that A is equal to the transpose. In fact, it is very clear to see from here that when you multiply, if you're trying to make A the subject of the formula, from this, when we start from P A equal to LU, when you multiply both sides by the transpose of P equal to PTLU, right? P times PT, because P is said to be a permutation matrix, and you can see here, it says since P is equal to the inverse of P, since the transpose of P is equal to the inverse, that means this becomes the inverse of P. Let me write it again. This becomes the inverse of P times P. If you see it clearly that way, P times the inverse of P times A equal to PT LU, and the inverse of P times P is always going to give the identity matrix. So this is I, and whenever I multiply I by a matrix, you get back the matrix A equal to PT LU. So this statement is the same thing as A, and that is the same thing as PLU. All right, that is a very powerful theorem. So let's go with this remark. Remark 2.3. The permutation P represents all the row interchanges performed during the GL with partial pivoting. The permutation P represents all the row interchanges performed during. So what it's saying is that all the rows in this matrix P, that is the permutation matrix P, they simply represent every interchanging of rows that you performed during your Gaussian elimination with pivoting. And I'll leave us. We're going to end this lecture today on this note, on example 2.3. We'll end it on example 2.3. So let's take example 2.3, compact LU storage. So after the LU decomposition with pivoting, let's say we have this matrix U11, U12, U13, L21, U22, U23, L3 1, L3 2, and so what's happening here? What this means is LU, right? That's what it means, a combination of L and U. And then we have our P, which is 1 3 1 2. The P here is the permutation matrix. If we separate it, if we separate this matrix into two, it represents L, which is this matrix, and U, which is this matrix, right? And then our P is going to be this matrix 0 0 1 1 0 0 0 1 0, and the original row that was performed is row 3 to row 1, and so on and so forth. So to obtain this answer here, all these operations have been performed. You know, that is what that theorem states, and the example has seen. All right, so like I said, we're going to stop here. I still have some things to discuss. By God's grace, by this Friday, we will complete the many things here, and we shall also complete the topic for week 3. And I will also upload the questions for week 2 on the website, as well as the materials for week 3 and week 2, so that we have access to them and you can go through them at your free time. So with this, we've come to an end of today's lecture. If you have questions at this point, I would like to take those questions. Thank you.